Yeah. Okay. Let's get started. So this morning's session is learning to rank with neural networks, and we have 4 instructors who are these people here, who are also these people up the front here, and 3 of us will be presenting the content this morning, and then Bhaskar and Daniel will be presenting the lab session in the afternoon, where we get to look at some of this stuff. But here's the our Twitter contacts and things like that. M&A is from University College London, and the rest of us are at Microsoft, but Bhaskar is also a part-time PhD student at UCL with M&A, actually. So that's the instructors. These are the resources for this. So these slides you can get from the top URL there, and there's actually a book that describes some of the concepts here that you can download as a PDF. And there's the lab materials, and there's a data set. So yeah, these are the resources. And I'm going to start out presenting the first part. Then M&A will present the second part. Bhaskar will present the third part. So let's get started with the first. A lot of this stuff just comes down to matrix operations, and so I'm going to assume that we don't have time to go through all of this in detail, but if you remember your linear algebra, or if you just want to take my word for it, a lot of the stuff that happens here is to do with matrix operations. So, for example, being able to sum matrix, being able to take 2 vectors and take the dot product, which is that you do an element-wise multiplication and then sum, and then matrix multiplication, where you do the dot product between each row and column to get the final result. And in fact, we're talking really about all of these things: the scalar, the vector, the matrix, and even if you add another dimension, then it's a tensor, which is like the 3D version. So it's like this, basically. Scalar, vector, straight line, square, and cube. So that's a lot of the underlying computation, what's going to be happening. And we're going to be talking about supervised machine learning, where basically you put some input, you're trying to produce some output, and you're trained to, according to some loss. This error signal we're going to call the loss is the training procedure. We're going to be talking about deep neural networks, and so what we mean by deep is that we're going to take this is the same as in the previous slide, we're going to take whatever input we have. So this could be text, it could be an image, it could be whatever. Like in our area, we do a lot of stuff with text, and then we're going to pass it through a number of layers in order to get some predicted output. And then we've got some ground truth training data that tells us what the desired output is. And like I said, the difference between the predicted output and the desired output is called the loss. Each of these layers does those kind of, can do those things like those matrix transforms or matrix multiplications that I showed a couple of slides ago. So it's basically applying some matrix operation. And in general, the pattern of this is to apply a linear transform, like a matrix multiplication, followed by some nonlinearity, followed by another linear, followed by another nonlinearity. The reason we do that is because if you just apply a bunch of linear transforms in a row, then that collapses down to just one linear transform. You're not really doing anything. So it's really important to have the nonlinearity periodically so that you're actually learning a more complex function. And so, for example, a nonlinearity could be something like you take the input and you apply a tan h function, which looks like this, or you apply a function called a ReLU, which looks like this. But it's basically some function that takes whatever, let's say you've got a vector, and you want to just do something to it to make it nonlinear so that the model can learn something more interesting. We're going to talk about the specifics of what these layers do, but that's really what we're talking about, these matrix operations, one after the other with linear and nonlinear in succession. And we're going to talk about how to then train the model to learn some target, using a loss, and using actually backpropagation of error. So that's basically what we're going to talk about. So let's say, so two things you might do. So like now again, we're doing the same thing. The loss is here in this diagram, and it's here in this diagram. So it's just the same thing again, but we're zooming in on that part. And so one task you could do, for example, is you could say, I want my model to predict a certain number. Like I want it to predict a number, and then it's going to, for a given input, it's going to predict a certain number, but I expected some other number, and so if these are different, that's the loss. Or you could do classification, which is very similar, except it's going to predict, are you in this class or not? In this case, for example, this is like a binary classifier, and in truth, it's this right one. The model predicts, that it may be this one, but there's some chance of it being that one. And so again, your loss is that you want the model to predict it's the right one because that's the truth. And in this one, you want it to predict a certain number in regression. So that's regression and classification. So I'm going to go through like how you would implement this this loss, right? So the first one is regression. Remember, where you're trying to predict a certain number. And a standard loss function for that is a squared loss. So the idea is that you've got a true value that you're trying to predict, and then you've got what you actually predicted. So that's the difference between, that's the true one here, and then what you actually predicted here. And you just basically look at the difference between that and square it, which has the nice property that it's not going to be negative anymore if it turned out to be negative. And that squared loss is for an example of what you would use in regression. You're just trying to get as close as possible to the true value, which is the same as making this quantity as small as possible. So that's an example of a loss. Before I talk about the classification loss, I want to talk about this idea of a softmax function. So here, we're maybe considering something that has 4 outputs, whereas here, in this case, I only showed 2 outputs. But it's this case of that you might use this in a number of cases, but let's say that there's 4 possible outputs in the case of the example here, and so your neural net is coming out with these numbers. But the numbers actually are kind of large. They sum up to some larger number because this one is above 6. It's hard to read the numbers here. Maybe this one's a bit below 4. This one's a bit above 2. So your neural net has produced some numbers, but you want to turn it into like a classification. So a typical thing people do is apply the function called a softmax. Softmax is this function here. And what it does is it just says, I'm going to transform each of these numbers by doing e to the number with a constant, but let's not focus on that. And then I'm going to normalize by the sum of the 4 things so that these all add up to 1. So you go from having something that doesn't add up to 1 to something that does add up to 1, which is good because you can now treat these kind of like probabilities. So this one is saying, with probability 0.8, it's actually class 3, and these other probabilities are less. And so the one thing it's doing is this normalization by making it all sum up to 1. The other thing it's doing is, again, dealing with negative numbers, and being easy to differentiate. There's a number of properties here that are useful, but but also it makes it more peaked. So basically, this one is kind of a bit higher, number 3 here, but when you apply the softmax function, you get this probability distribution where there's a bit more of a peak on the one that was largest. So it's kind of, that's why it's called a softmax, because it's like saying here, number 3 is the max, which is what your network actually produced, but we're just going to apply a function that actually makes, it's really emphasizing the maximum value here, which in this case was 3. So let's, in classification, we might apply this, very common to apply this softmax function. And then the nice thing is that fits in really well with this idea of a cross-entropy loss. The cross-entropy over probability distributions is like an information theoretic thing, but just think of it as, it's like, in truth, I know, again back here, right? I know the truth is, of these two things, the truth is, the expected, so expected, right? The truth is it's the right one. The predicted is that it's probably the right one, but it's a bit smooth because I've done the softmax here. The cross entropy says, how close am I to correct on this prediction? In information theory, it's to do with how many bits you would need to encode the difference. But actually, because in truth, it just is one of the things and not the others, it actually just comes down to saying this thing, which is like how much, after I do my, in the case of the softmax, after I do my softmax, how much probability am I giving to the correct answer is basically, or minus negative of that, right? Yeah. Okay. So this is a kind of standard thing people do, is that they'll take the outputs of their neural network, they'll apply this softmax function, and then they'll do the cross entropy loss. And it looks like this, and that's a standard thing that people would optimize for, not only in classification, but in other areas too. So now we've talked about the loss, we talked about the squared loss, and we've talked about the cross-entropy loss. So then how are you going to learn now that you've got this loss? So this is just an example of how you could learn given a loss. In this case, the loss is going to be on a regression task. And so the way it's written here, the loss is the squared error that we talked about for a regression task. And we've got a neural network that takes an input. I hope it's not too hard to read. It basically applies a weight, wx plus b, to this x. Then does a nonlinearity, which is the tanh. Then it does, again, applies wy1 plus b, or different w, different b, to get the next layer. And then we're going to see our loss is like how well are we predicting this output? Is the number close according to our squared loss? So basically, and what you want to do is you want to learn your w's and your b's such that you get the right answer. And in particular, you want to know how to update the w's and the b's in order to do the right thing here. So let's say actually the step here that you do to train is at the bottom. It's based on gradient, which is why it's called stochastic gradient descent. It's called stochastic because you're going to do it on a subset of the data each time, which is not an important point to go into here. It just means you don't have to take your whole data set and work out the gradient. You just do it one batch at a time. That's the stochastic part. But basically, the key thing you need to figure out here to learn, let's say W1 is the one you want to learn, which is the first weight that was applied here. Is that you want to figure out a gradient that tells you how to update W. So the old W is some learning rate times the gradient to get the new W. So there's kind of a parameter there that tells you like how fast you should adjust. And if you do any kind of like experiments with deep learning, always look at the learning rate. It's like a huge thing that is can be wrong or can be tricky, or you can have problems there. That's always a key thing to look at. But basically, to update the weights as you train, you need to figure out a gradient, which is how does the loss change for this, I'm just going to say D, DL, DW1, is the, how does the loss change when I change weight 1? And so then to actually figure that out, there's this kind of stuff, where basically you can decompose the gradient into the what happens at each step here. So how the loss changes with W1 is, which is how this loss changes with W1, which is way back here, depends on how the loss changes with respect to Y2, and it depends on how Y2 changes with respect to Y1, and it depends on how Y1 changes with respect to this W. So that's the kind of thing. Now, luckily, you don't have to do all the differentiation to get this gradient. There's kind of toolkits that let you do it. But just to work through an example of what the tool is, mathematically what's happening, we can start replacing things. So we can say the gradient, how does L change? Well, what's L? It's the this squared error. Then how does what happens if I differentiate that? Well, when you differentiate this thing, it actually looks like this. Then replace the next thing, and what happens when you differentiate that? It looks like this. And actually, there's more going on here that we're kind of skipping over. But basically, you can basically figure out, what is the gradient of the loss with respect to W1. And in this small example, it tells you how to, in this toy example, it tells you how to update W1 using a learning rate. So I won't go more into it than that. But basically what it means is that if you're using one of these toolkits, how you can think of it is that you're going to just build a sequence of matrix operations where actually, luckily for us, the toolkit knows how to do all the differentiation, but you can put together a thing where there's, our x was going in at the bottom, and we've got an error at the top, and we're basically going to learn by composition of all these parts. That's how it looks from more of an implementation point of view. And yeah, the two things it needs to be able to do is a forward pass, where it takes your input and produces the output. So in this case, it's like it takes the x and produces this y2, then figures out the error, then does a backward pass to figure out the gradient and how to update the weights. So this is what the toolkits are doing for you. This is a slightly old slide of listing a bunch of different toolkits, but for example, a key one to look at is PyTorch. That's become quite important in research, and we even use it in the product as well. So all of this stuff I just showed you about how you put together a network, you could do in PyTorch. This example is some example code. We don't need to go through it, but in the lab, we will go through examples, two examples that have this sort of form where you have some code that describes the model architecture, some code that describes the loss function, and then you loop over your data and you train. So that's just how you code up one of these things, and that's what will be seen in the lab. So one of the interesting things here is that basically there's kind of an arms race to see how deep people can make these deep neural networks. And people are spending a huge amount of money on getting hardware acceleration, like GPUs and all this kind of stuff. And so, for example, I work more with text. So with natural language processing, everyone's trying to train these larger and larger models with like a billion or billions of parameters. And the reason they do that is because it actually just seems to work better as you make the model bigger, which is kind of interesting. So we're going to talk a bit about that and why it could help. in fact, that's kind of mainly what I'm going to talk about now, is just some intuition. Like, why would it make sense to make this model bigger and bigger? Like, what is going on here? But definitely the case is that for speech recognition, for images, for text understanding, all these cases, we've been finding that making bigger and bigger networks is a good idea. But just again with like a small toy example, just to give you an idea of like how you could learn a more interesting function using a deeper model, then just imagine this example, okay? So this is a really simple example. You've only got 4 words, which is surface, Kerberos, book, library. And you're trying to identify, is a phrase that I see related to tech or not related to tech? And there's 4 possible phrases. The ones related to tech are surface book, which is actually like this. Machine is some kind of surface. Or Kerberos library. Those are tech related. But Kerberos surface is more like, I don't know, astronomy or some kind of like, or library book also is kind of a different topic, let's say. So we're trying to tell the difference between these 4 phrases. The problem is that if you only know for each example, so each of these 4 examples could be these 4 rows, right? So there's 2 that we want and 2 that we don't. It's actually impossible to come up with a set of weights over these 4 features that gives you this classification. Yeah, the problem is if you say I like surface, then you equally get surface book and Kerberos surface. And if you say I like book, you equally get surface book and library book. Like whatever you do to put linear weights on this, you can't separate them. You can't, this is a difficult classification problem for linear, impossible actually. So just to illustrate, if you add an extra layer, what you can do is you can have, so this is, we're talking about the layers and the nonlinearities again. If you basically have a, this thing gets activated, I guess, by surface and Kerberos, is that right? And this one gets activated, surface and book, sorry. And this one gets activated by Kerberos library. Like basically you can decompose the problem into finding one of the items you want and the other item you want. And you can basically come up with a classifier that can separate these cases where it was actually impossible to do with a linear model. So it's kind of decomposing the problem into, it's almost like feature generation. Like now you've generated a feature that combines the features in an interesting way and another feature that combines the inputs in a different way. And using those together, you can do more than you could do if you were just consuming, with a linear combination, the input features. So basically, this hidden layers that we learned can actually identify the 2 cases we care about. Yeah. Oop. Let me see if I can make sure this is going to play. So this is an animation. I'm not sure how easy it's going to be to see, but what it's doing is the inputs are just the x and y coordinates of this space. And the outputs are, do you think you're in an orange area or a blue area? And the training data are these spirals. So there's a blue spiral and an orange spiral. And so what's happening is this one has got one hidden layer, and it's kind of learning combinations of x and y, and it's trying to combine them, and it's trying to find this shape, but it's actually quite difficult. Whereas, yeah, in this animation, this one with 3 hidden layers has actually managed to find, it starts with just like x and y are like, it's hard to see perhaps, but there's like a vertical and a horizontal distinction when you look at x and y. These are more like diagonals, but each layer learns more and more interesting shapes, and by combining these interesting shapes, you can actually learn something like a spiral. So a difficult to learn function can be learned using more and more layers, basically. So it's just, that's one argument for why it's good to have more depth, because you can, now theoretically you can learn any function if you have a wide enough network as well, but like yeah, this is one example where depth helped for fixed width. Another explanation that's like, so this is quite recent, is that if you take a, let me see, maybe I should just play the video and see if I can talk through it. So let's say you're training a neural network again, so we've got inputs and outputs, and maybe these are indicating the weights or something like that. And as you train, you actually learn some good weights, and you get good accuracy. Then you prune the weights once you've done that, okay? Now I'm gonna, so what I've done is I've learned a full network, then I've pruned away the weights that didn't seem to help, because, you know, there's ways of basically pruning weights. And now I'm gonna train using just the remaining edges, but the key thing is the same initialization. So the observation of this paper is that I can get rid of a lot of the connections here and a lot of the complexity and still do well. So that's what that was just showing. Whereas if I started from a random initialization with that was pre-pruned, I couldn't do nearly as well. So the lottery ticket hypothesis is that within this like random initialization that I started with, you know, if I just train, I can do well. Then I can prune. As long as I start from the same initialization, I can also do well. But if I just start from a pruned random initialization, I can't do well. So there's something about how the training procedure is actually finding within the initial setup a set of a part of the model that's useful for solving the problem. So like one reason it might be good to have these big networks is because hidden in the initialization are some, like, because you randomly initialize these neural networks, and maybe in the random initialization there's a solution, and maybe what neural network training is doing maybe is finding this lucky random initialization, and that could be a reason why it's a good idea to have these giant networks, because you're just hoping that somewhere in there is a solution, and you're hoping that you can find it using the training procedure. So yeah, this is some quite recent work on why this stuff might work, is that it's identifying these lucky parts of this giant randomly initialized thing. One of the other weird things about this, so when I was talking to a colleague of mine who's a machine learning guy, he said one of the few things he would teach people about machine learning was the bias variance trade-off. And so this is the idea, and I'll go into details of what this means in machine learning, but if you just look at this example that isn't machine learning on the right here, if you have low bias and low variance and you're trying to shoot at a target, you just always hit the target. If you have high variance, you're kind of centered around the target, but you are more spread out. So that's what variance means. I'll show you in the next slides what it means in ML to have high variance. Or if you have high bias, that means you've got a small you've got a small target, but I don't know why my pointer went away. Yeah. Anyway, you've got a less spread, but at least but you're kind of missing the bullseye, and then high variance and high bias is that you're just completely off. And so in machine learning, they say there's this bias variance trade-off. It's hard to have you have to choose between the two. So I just wanted to give you a feel for that, and then talk about why this might be even slightly different in deep learning. But like just for really simple examples, the very standard thing that everybody could look at in machine learning. So imagine I'm actually just generating some data sets here. And what I'm doing is I'm getting 20 x values. Each point of these is one of them. And I'm making y squared plus noise. Y is x squared plus noise. So it's kind of like a curve. And here's 3 different samples. So when you're working with data, don't think of like, here's my data. Think of like, I have a procedure for getting data. And if I did it 3 times, I would get different data, but there's some underlying structure that I'm trying to learn or study, or model, actually. So, I've just got this toy example where it's kind of y equals x squared, but there's some noise. And why is there noise? It could just be because there's noise in my measurement. There's something going on that I don't understand. Like it's rarely the case in real data that everything lines up perfectly. So I just added some noise to represent that kind of issue. So again, in the standard way of looking at things, the bias variance trade-off is as follows, right? So what I've done here is this is a degree 0 polynomial modeling the data, and it's terrible, right? This is degree 1 polynomial, degree 2. So degree 2 means it's got an x squared in it. Degree 3 means it's got an x cubed in it. And this is then 5, 10, 15, 20. So what the bias variance trade-off usually means in standard ML is that, in some sense, this is a pretty good model. This one, like the degree 2 polynomial, it's kind of fitting the data quite well. And actually, we happen to know that underlying is y equals x squared. So it's actually kind of modular noise. It's actually correct to some extent, but it's biased because it's missing a bunch of the points, right? So it's not quite correct. It's not modeling the noise very well. Whereas this one, the degree 20 polynomial, is going all the way through all the points. So it's actually a very powerful model. It's learning, and so the standard story in machine learning is that you could either have this one, which is biased, or you could have this one, which is less biased. But what they mean by variance is that if I sampled another set of data and did exactly the same thing, then this one, it has less variance, because in both cases, it's roughly the same line, even though the data changes. Whereas this one has a lot of variance. So like it changes a lot every time, right? And so this is what they mean by the bias variance trade-off, is that you could either have one that's consistent across samples, but doesn't quite go through all the points, or you could have one that goes through all the points, but it's less consistent between samples. And usually we think of it as being a trade-off between these two cases. And that's a fundamental thing that everybody knew about in machine learning. So the weird thing that's happened lately is people have noticed that these deep models are super powerful. So they're kind of like this degree 20 polynomial. They've got a huge amount of capacity. And the question is, like, why do they work, right? Because this bottom right one kind of seems like it's not a good idea to learn a model that's this bouncy, this much variability. Why does it work? And that's been a mystery for the last few years. Like, I remember in 2016, I put together some slides on this when we didn't know. We know more than we did then, but we still don't know. But one paper I could point you to is this recent paper. And what they did was they showed, at least empirically, so basically I should have given you this detail, but basically our degree 20 polynomial is like the one that's out here. This is the traditional way of looking at it. I don't know if it's, I might regret this if I better not. I don't know if I regret this. The traditional way of, oh, damn it. Okay. So this is the one where, as we got up to degree 20, it was doing perfectly on the training risk, but it was actually really bouncy, so it probably wasn't going to do well in your test set. That's the traditional way of looking at why it's bad to do the degree 20 polynomial, the really bouncy one. But actually, if I look at empirically, this paper is saying, well, there's some kind of hump here, and as you get to a certain stage, your test risk starts going back down again. And there's some theories about why there's this strange kind of, I don't know, W or partial W kind of shaped curve. But at least empirically, we're seeing that just adding more and more capacity seems to be working. So this is one of the most surprising things. So basically, to sum up, what we've done is we've talked about like these deep models that are matrix operations, and they have linearities and non-linearities. There's toolkits that help you do it, so you don't have to do the differentiation yourself. And for some reason, making the neural network really big seems to work really well. And we're not entirely sure why. We know that we can, sometimes it can be easier to learn a more complex function as you get deeper here. We saw the lottery ticket thing that said maybe hidden in a giant randomly initialized thing, there's a solution or something that can be made into a solution. And then this one is saying basically, and maybe this deep learning stuff has actually turned our previous theory on its head, because we're actually finding that we can make the model way more complex in a way that would have been a terrible idea, because it's like this bottom right one from this slide in our previous models. But somehow with these deep models, it's turned out to be a good idea to add more and more capacity. So that's just like an overview of what is a deep model and some ideas on why we think it works. So I'm going to hand over to the next speaker.
This is the scene, fixing the middle of adding.
Yeah, I think that this is, when they say, they're making the model more powerful in some way. It could be more layers. Yeah, I don't know if you remember the exact experiments.
Yeah, the number of layers, the number of parameters, the parameters.
Yeah, and they've got some proof of this as well, and they've got some theories about why it's happening. But it's very surprising. And people have been noticing it for a few years and had a few ideas of like why it happened. I'm still not sure we've nailed it, why it works.
In practice, the plot may not look like this. It might look something like this, but it has some, and still has very
Yes, that's it. So I should have used the term, Bhaskar was telling me yesterday, remember to say the word overfitting. I forgot. But yeah, that's right. So it used to say that this one, this one on the bottom right, and then somehow with the deep
I guess everyone can hear me. Okay, in this part of the lecture, we are going to talk about learning to rank. So in the first part, we mainly focused on machine learning techniques, and it was kind of an introduction and motivation. So you cannot hear me? Is it better now? Okay, sorry. Okay, in this part of the lecture, we are then going to focus on learning to rank, where the goal is to build machine learning algorithms that can learn to rank a set of items. So why learning to rank? In lots of settings, you are faced with the problem of providing a rank list of items. And if you are, for example, using a search engine, given a query, you are supposed to return a rank list of documents. Or in a recommendation setup, when you are looking for, when the system is showing you similar items similar to the one that you have seen, usually the system is trying to rank recommended items in terms of their likelihood of being similar to the item you have shown interest to, and so on. So like in YouTube searches. So in practical applications, learning to rank is an approach that is very commonly used, which is the task of building a machine learning algorithm that is trained to learn to rank a set of items. So there has been quite a bit of research in learning to rank, and these approaches that are based on building machine learning algorithms that can learn to rank a set of items have been shown to perform very well in practice. Therefore, lots of models that you currently use in your everyday life when you access search engines and so on, they are based on some variants of these learning to rank approaches. And there has been some competitions like a Learning to Rank challenge where the goal was to kind of compare or compete against other learning to rank approaches using very large data sets and so on. But what I'll talk about now is basically what are these approaches that are commonly used for learning to rank and what are the principles behind them. So before we start, let me give you a formal definition of how learning to rank, what is learning to rank, how is it defined? Learning to rank is defined officially as the task to automatically construct a ranking model using training data such that the model can sort new objects according to their degrees of relevance, preference, or importance. So the definition you can see here. And this is exactly the definition we will also use in this part of the lecture, and that's what we are trying to achieve, to build a model that has this property. And the way it works usually in practice though, a typical learning to rank system is kind of used in two phases, where in the first phase you actually have a candidate generation phase. And what we mean by that is, given a very large collection of documents, let's say you are building a search engine and you have a huge collection, like the web, for example, the first phase is to generate candidates from the web. So you don't apply learning to rank method at the time normally. What you do is you apply a very basic retrieval function, like we have learned about BM25, for example, or language models. So these very simple retrieval models, because they can run on very large collections much more quickly and return this candidate set of documents in a quicker way, they are the ones that are used to generate these first candidates that are then usually fed into the phase 2 ranker, which is based on usually a learning to rank approach. So the learning to rank methods are quite often run on some candidate set of items that have already been generated using some initial retrieval model. And what type of information do these learning to rank approaches or the initial rankers use? They usually use some information about the query and the document contents, as well as some information about user history and context to perform this retrieval, which we will discuss more in a bit. Okay, so let's try to give a more formal definition of what we are trying to do in learning to rank. So how do we represent the items? We have a set of items in learning to rank. How do we represent them? In context of learning to rank, a rankable item, like in context of search, it's a document. Given some context, it's represented as a numerical vector, where each dimension of this vector could correspond to like a different feature associated with this vector. And we'll discuss about what type of features are commonly used in learning to rank in a bit. Then our ranking model, F, is a mapping between this feature vector X to some real valued score, so that our ranking model is basically trained to map this vector to a real valued score, such that relevant items are scored higher than non-relevant items. So in the training phase of these learning to rank models, you oftentimes assume that you know the relevance of items, meaning you actually have them annotated. So you have these data sets where some annotators have sat down and labeled these documents as relevant or irrelevant with respect to the queries that are in your training set, so that you can train these models using your relevance labels. But it doesn't have to be just relevance labels. If you have access to click logs, for example, these could be the labels that you train against, like try to rank items that are clicked more often, or that are preferred more often than others, higher in the list, for example. But the assumption again is that during training, you know the relevance labels for documents and queries. Okay, so one question you may ask is, there are all these, in the first part of the lecture, we talked about basic machine learning approaches, like classification, regression. Why are we specifically talking about ranking in this part? Why do we need a separate discussion on learning to rank approaches? And why do we need different models for learning to rank? One of the primary challenges in learning a ranking function is that you ideally, when you learn a ranking, when you train a model to generate a ranking, you ideally would like to train a model that can optimize for a rank-based metric. You have seen in the evaluation lectures several metrics that evaluate the quality of a rank list of results. So ideally, if your goal is to produce a perfect or really good quality ranking, what you would like to do is to build a model that can optimize for this quality evaluation metric that you have, the quality of the entire ranking. But one challenge with that is these metrics, since you have learned these metrics like NDCG, average precision, and so on, they are the metrics that are assumed to be evaluating quality of a ranking. So we need our model to be able to optimize for these metrics like NDCG. But the main challenge in learning to rank is that these metrics are not smooth or non-differentiable. And what do we mean by that is if you think about how ranking works or how these metrics are computed, is you generate some sort of scores. Let's say you have a learning to rank algorithm. It generates these scores. And then based on these scores, you can produce a ranking. But when you try to optimize for one of these ranking metrics, you have to do a sort operation in terms of these scores so that you can assign ranks to each of these candidate documents. And based on these ranks, you compute these scores. But now that you have gone through this sorting and ranking operation, your metrics, your metric values with respect to the scores you have generated have become not differentiable. And because of that, as you saw in the first part of the talk, like Nick was talking about, when you do a training using gradient descent, for example, you would oftentimes do backpropagation, where you compute the gradient of your cost metric with respect to each of the weights in the previous layers, right? That would require computing a gradient of your metric score with respect to these weights, which is a challenge when your metric itself is not smooth or is not differentiable. So that's the problem that we are faced when we try to build a machine learning model that optimizes a rank-based metric. Okay, so given this challenge, what we'll do now is we'll first talk about what are the features that are commonly used when building a learning to rank algorithm. And then we'll talk about, given this challenge of dealing with non-smooth cost functions, how do we deal with this challenge and what are the different approaches that people have used to overcome this challenge. But first, let's briefly talk about what are the features that people have come up with when they build these basic learning to rank approaches. So these features can often be categorized into three different categories. One is query independent or static features. These would be the features that would mainly depend on the document itself. They are completely independent of the query. So a very good example of such feature would be like the PageRank score, which is kind of a measurement of how authoritative or how much you can trust this particular document regardless of its query using the in-link structure. And you can also use other features like incoming link count and document length and so on. And we also have like query dependent or dynamic features. And these would be the features that are based on how similar is this document to the query. So you have already learned these very basic retrieval models like BM25, and you can use BM25 as a feature in your learning to rank algorithm, or you can use other language modeling-based approaches as features as well. And finally, you also have query level features like query length, for example, and these are also important to decide what type of documents are expected from this type of query and so on. So here's a table that shows a summary of features that were used in LITER, which was a benchmark collection that was used to kind of promote research in learning to rank. So LITER was a data set that was provided. It's a training and evaluation data set, standard data sets that was commonly used by lots of researchers to build their learning to rank algorithms. And it's relatively small. As you know, deep models now require lots of training data to be trained. So at the time, when it was proposed, we didn't really have deep models for learning to rank. So right now, it's a very small data set if you want to train a deep model. But lots of machine learning algorithms for learning to rank, they were really using LITER, and it's still commonly used if you are building standards like non-neural learning to rank approaches. So let's briefly take a look at the features that have been used in LITER, because they give you an idea about what type of features you could use when you train your own learning to rank algorithm. So there are various features. One of them is based on like number of times a query term appears in like the body, anchor, title, and so on, different fields of the document. So you can separate body, anchor, title, and so on, which is a common practice actually in IR. You treat the title, body, and anchor, and so on differently, and you compute features for these portions differently because they tend to have different importance in terms of ranking. And now we have the immersed document frequency. These are features like 6 to 10 for the query terms in body, in anchor, and so on. Then we have several features that are combination of the term frequency, this is the count, which is TF actually, of query terms in various portions of the document, and times the IDF of these terms. Then we have various length-based features like body, title, and so on. Then we have various basic retrieval model-based features like BM25, or we have language modeling, LMIR, with different smoothings like absolute discounting, Dirichlet smoothing, and so on. And then we have several hyperlink-based features. Like once you have computed the page rank score, for example, of the document, you can use that as a feature, but you can also propagate back the page rank score to documents that link to that document, or that this document have outlinks to, for example, and use those values as features as well. So these are the sitemap and hyperlink-based features. Then we of course have the hits and page rank scores themselves as features. Then we also have the topical versions of these. I don't know if you covered that, but typically when you compute page rank, it's independent of the topic. So you just run it in the entire web, for example. But quite often, what is an authoritative resource in a particular topic could be different than when you consider that specific topic versus the web. So you can also do like topic-specific versions of these. And we also have like outlink numbers, number of slashes in the URL. Does it go way too deep, or is it like the root URL, number of child pages, how deep is it? And again, some other BM25 and language modeling-based features. So this I hope gives you an overall idea about what would be some reasonable features to use if you want to train your own model using a learning to rank approach that requires this feature extraction or feature engineering.
Sorry, just curious as to what the difference is between look at the BM25 features, count the URL, for instance. Which one between?
Yeah, so have you learned about 22 and 24, right? Okay, so do you know what anchor text is? Have you learned about it? No. Okay, what anchor text is, let's say you have a text that says if you are interested in learning more about neural networks, click here, for example. Or this is the link to learn about neural networks, where you just have the link to click on. And that text describes a lot what the target URL is about, right? Because there is another document that specifically says for neural networks, that's the target URL. So this link, this text description that you have here is the anchor text for the target URL. So that's the difference between the URL itself for the destination versus anchor text. Yeah? Okay. Okay, so now we have the features computed for our documents, and we are ready to do our training. So what type of models can we use for learning to rank? There has been lots of research that people have done for building these learning to rank models. And in general, most of the learning to rank algorithms can be categorized into three types. The point-wise approach, pairwise approach, and list-wise approaches. So what is the pairwise, point-wise approach? As I mentioned, in training time, when you are training a learning to rank algorithm, you would have a data set that contains the relevance label of the document with respect to the query that you have. And in the point-wise approach, the goal is you basically have a regression or a classification model that is trained to directly predict the relevance of the document with respect to the query. So directly point-wise, for each point or for each document, you are trying to predict its relevance. Then we have the pairwise approach, where instead of an individual point or individual document, you consider a pair of documents, and you try to predict, is this document more relevant to my query than this one? So in these models, your input is actually, instead of just one document, is a pair of documents, and you try to predict which one is better. And if you think about it, this could actually, this can kind of reduce to binary classification, where the classification task is to predict, is document I better than the document J, which is kind of label 1, or the other one is better, label 0. So you can think of it as a classification task. Then we finally have list-wise approaches, where the goal in here is to directly optimize for a rank-based metric. Like, assuming that all these ranking-based metrics that you have learned in the evaluation lectures, they are direct estimates of ranking quality. The goal in these list-wise approaches is to directly optimize for these rank-based metrics. One challenge with this one, like we discussed before, is the fact that these metrics are not differentiable. And in fact, these approaches tend to work much better than the others, but some of the other approaches were initially proposed because of the fact that these metrics are not differentiable. So they were just using these initial basic models to kind of use to predict directly relevance instead of having to sort the scores and so on. So let's start. Now what we'll do is we'll go through all these three approaches, and we'll see some basic examples that people have used from within these approaches. So in terms of point-wise objectives, again, the goal is basically to learn a model, machine learning model, that can predict directly the labels for each document. So the label here can be binary, like relevant, non-relevant, or in some cases, they could also be multigraded, so 0, 1, 2, 3, for example. And quite often, the way these models work is that you would basically, your final cost function would be square loss of your actual relevance label minus the relevance label predicted by your system, and you would compute the square loss between the two and optimize for the square loss. So it's a very basic regression model, basically, that you have learned in the first part. In point-wise objectives, you can also cast it as a classification problem instead of regression problem. So now, if you have two kind of labels, relevant and non-relevant, in a sense, you have two classes. So your goal here is to predict whether you should assign each document to the relevant class or non-relevant class. So basically, in this one, again, you have seen in the first part, Nick showed how we can do classification. A common used approach there is to first do softmax, so you form a distribution over the different classes that you have. And then at the end, your loss function would be the cross entropy between your actual labels and the distribution that you have obtained after applying softmax on your scores. So then our cost function that we have here would be our cross entropy loss with softmax. Okay, again, this is a basic classification technique, but applied to learning to rank. Finally, now, so these were very basic point-wise approaches that just use standard machine learning techniques, but applying them for learning to rank. But what could do better is, in case of learning to rank, the task is more like kind of trying to decide which item should be ranked above the other. So what is a better item than this one? If you think about it that way, a more intuitive way to train a system would be using pairs. Therefore, people have proposed using pairwise objectives instead of using these pointwise objectives, where the goal in this case would be is to minimize the average number of inversions in the ranking. So what we mean by that is, let's say you have a pair of items, di and dj, for which you have relevance labels. And based on these relevance labels, you know that document I should be ranked above document j, because I is relevant, j is non-relevant. You should train your model in such a way that your model also predicts that document I should be ranked above document j. So in this case, instead of just giving one input, document I, to the system, we input two documents to the system, document I and document j, and the system outputs some score for both of these documents. And then our cost function is a function phi of the score differences between the two documents. Okay? So there can be various ways to compute this function at the end. Some people propose to use like the hinge function, which is maximum of 0, 1 minus z. As you see, we want z value to be higher here because I is supposed to be more relevant than j in the training data. So, and all these functions, so you could use like exponential function e to the power minus z, or logistic function, which is log of 1 plus e to the power minus z. All these functions have the property that as z increases, their value goes down, as expected. So, again, depending on which one, what you would like to do, you could use any of these cost functions. So one very commonly used metric, one very commonly used algorithm for learning to rank is RankNet. This was one of the original learning to rank methods that seemed to perform extremely well, and it's based on this pairwise approach. What pairwise does is kind of based on first compute what is the probability, given the scores that are output by my system for document I and document j, what is the probability that my system would rank document I above document j? And in RankNet, this is computed by using this logistic function, which is 1 over 1 plus e to the power minus gamma times the score differences. Okay, so they took this logistic transformation to convert these scores, the two scores, Si and Sj, to convert it into a probability value, which gives us the probability that I is ranked above j. Then we also have the actual real probabilities, where, as we were showing in the previous slide, document I is more relevant than document j. That's the assumption. So for actual probabilities, Pij would be 1. I is definitely better than the other one. And Pji would then be 0. So what they did in RankNet is, given these predicted probabilities and desired probabilities between document I and document j, they just computed the cross entropy between P and P hat, which is the RankNet cost. Okay? So if you were to write this cross entropy between P and P hat, what would happen is, this is how the formula looks like, which Nick has described before. And in this case, as we know, Pij hat is 1 here, but Pji hat is 0. So this part would disappear. So we just have minus log of Pij, which is this value here. So we just have to compute this value for document I and document j. An extension, so RankNet here is just based on pair of items. An extension of this one would be, instead of just considering pairs, you could do the same training where you consider one relevant document against a bunch of non-relevant documents. So instead of having to do it over pairs, you can do it several documents at the same time. And that's the more generalized cross entropy loss, but it's based on exactly the same kind of idea and assumptions as RankNet. So instead of in the previous case, very similarly, now we have multiple documents at the same time. So we have to compute a probability distribution that one document is better than the other. And you can use the softmax here again. And then at the end, you again compute the cross-entropy loss between your actual labels and your output scores. So it's the same idea, but now you have multiple documents at the same time, which can be more efficient for training. Okay, so this was the pairwise approach. And the final category of approaches that we have, and these are the ones that tend to perform very well, are the listwise approaches. Okay, so what these listwise approaches try to do is to directly optimize for some evaluation metric that is assumed to be evaluating the quality of a ranking. Okay, so let's assume that you have these two rank lists and you have these blue documents that are relevant. In the previous case, we were focusing only on pairwise errors, and we were trying to fix these pairwise errors. Okay, but in this case, you have quite a few pairwise errors because this item is ranked above all of these non-blue items. But if you look at number of pairwise errors, the pairwise errors in this case is actually lower than this one. Sorry, higher than this one if you consider all the pairs. But in terms of quality, this one is actually better because we have the relevant document ranked at the very top. So the number of pairwise errors that you count doesn't necessarily reflect the quality of exact ranking. Again, when you are doing learning to rank, usually the goal is to rank the most relevant items at the very top end of the ranking. And the reason for that is because users tend to look at items from top to bottom. So getting this very top item at the very top right is really important. Therefore, we need a metric, a loss metric, that also has higher quality score in this one compared to this one. But if you were to just look at a pairwise metric, that would have a lower quality score, this one, compared to this one. That's why using the RankNet objective of just using the pairs is not ideal. We need a metric that really would give much more weight to getting that top item right. And that's the reason why people started looking into switching from these pairwise ranking models towards ranking models that directly optimize for these rank-based metrics like NDCG or average precision. So I was told that we have a break in 1 or 2 minutes, like quarter past, is that right? Okay, so maybe it's worth kind of giving a break here, because in case there are any questions, we still have 1 more minute before the break, and we can continue after the break. Yeah, they are the scores that your model generates for this document. In classification, final score. You pass through all the stages, like if you have a neural network, it's the very final score that your model has generated before you pass it into any of these logistic, whatever functions.
So even in the pairwise network, you will have 2 scores.
Yeah. In pairwise model, you always have 2 scores, yes. Score for document I and for document J.
Okay, you explained some approaches earlier on, the point approach and all that before the pair one. And then you said the reason why those approaches came is because of the challenge with the pairwise, because the metrics are not differential. Okay, and then you went on to introduce some models like the RankNet loss. I'm sure some models there that okay. What is not clear to me is the function in these models, especially like this ranking net loss and the cross entropy, the function that is actually helping to solve the problem.
Yeah, to smooth them.
Non-differentiation of those metrics. That's not clear to me.
So in these ones, you are not dealing with metrics at all yet, right? The models we have talked about until now. You are just dealing with scores, and on top of these scores, you apply some transformation that converts to these scores to some distribution if you are because at the end you want to kind of have a distribution if you are casting it as classification or kind of binary preference one, right? So that's why you don't have to deal with the fact, the reason why this non-smoothness appears is due to the ranking part. But in these models that we have discussed until now, there is no ranking. There is just a score output, and then you feed it back. So it's very similar to the models that you saw in the first part of the talk by Nick. That's why you don't have those issues yet. But now, after the break, we'll talk about models that deal with directly optimizing for a rank-based metric, where that becomes a challenge, and we'll see how they deal with this problem. Sure. Okay, let's have a break now then, and we'll be back after the break.
And then subject metrics.
No,
Hello. Can I start? Okay, guys, let's start the second half of the lecture. So before the break, we were talking about the point-wise and pair-wise approaches to learning to rank. And one second, I have problems with the microphone. Can you all hear me? 1 second. How about now? No? Yeah? Okay, great. Okay, we were talking about the pairwise and the pointwise approaches to learning to rank, and we had just started talking about listwise objectives. And the motivation we had behind listwise objectives was that if you look at just pairwise errors, they don't really reflect the quality itself, which is the ranking quality metrics itself, which tend to be top heavy because most people tend to care more about the top end of the ranking as opposed to bottom end of the ranking. So ideally, we need some methods, learning to rank approaches that can directly optimize for metrics that evaluate quality of a ranking, such as NDCG and average precision and so on. Okay, but as we have discussed before, these metrics that are based on ranks of documents tend to be non-continuous, because of which they are non-differentiable. As you saw in the first part of the talk, in order to do backpropagation, we need to compute the gradient of loss function or the scores with respect to the weights of each of the layers. And when our loss function is non-continuous and non-differentiable, that becomes a challenge. How do we then optimize for these metrics that tend to be non-smooth? So one approach that was proposed for that purpose is lambda rank, which is one of the best performing learning to rank algorithm for a very long time. And it was one of the winners of like the Yahoo Learning to Rank Challenge. And even until now, some of the commercial algorithms are still, that you use are still based on, some of them are still based on lambda rank. So how does lambda rank work? It's based on one primary assumption or observation, actually. So what they said is that instead of starting with this objective metric, the cost function itself, which seems to be non-smooth and differentiated backwards to do backpropagation, why don't we directly start from how the gradient of this loss function should look like? So they didn't really look at the cost function itself and compute the gradient. What they said is that let's try to see how these gradients, or what type of properties should these gradients should satisfy, and let's directly try to kind of come up with some gradient values for documents I and J. Okay, so basically, if you have document I and J, again, it's kind of looks at pairs in a ranking, but it does it in such a way that these pairs of documents get a higher weight if they are making errors towards the high end of the ranking versus bottom end of the ranking. So basically, one thing that our gradient for a pair of documents should satisfy is that the gradient should be higher for pairs of documents that produces a bigger impact in NDCG, for example, if we are optimizing NDCG, by swapping positions. Okay? So if you have two documents, I and J, if your NDCG score changes more when you swap these documents, then the gradient for those documents should also be higher than having another pair of documents for which the change in NDCG score is lower. Which means that if we have two documents at the top end of the ranking, which are erroneous, for example, so we should swap them, then such an algorithm would give a higher weight to those gradients of these documents compared to documents that are kind of ranked in error towards the bottom end of the ranking. So that's kind of the main assumption behind lambda rank. There is no theoretical kind of derivation of why this would work. It's a little hacky actually. It's just based on this observation, but it works really, really well. And in fact, people have later on showed empirically that by using this approach of defining gradients directly instead of computing gradients from the cost function backwards, you can actually optimize for the objective metric itself. So people have further experimentally validated that by using this approach, you are indeed optimizing the objective metric. So then, how does it work? Basically, in order to compute the gradients, basically they said, okay, the gradient of lambda rank at a particular point for documents I and j would be the gradient of lambda rank cost function, which we have, so rank net cost function, which we have seen before, the pairwise approach, times the change in NDCG score if I were to swap the positions of documents I and j. Okay? So in a sense, lambda rank is still a pairwise approach, but it is optimizing a rank metric, rank-based metric in the entire list by computing the change in NDCG score for the entire rank list of documents, but if you were to swap the ranks of these documents I and j. So that's how the gradient of lambda rank is defined. Again, it's a little ad hoc, but it works. It seems to work extremely well. Okay, so lambda rank, like I said, is one of the most commonly used. Was one of the most commonly used approaches. Now it's slowly getting replaced by some neural models in ranking, which Bhaskar will talk about in the later in this lecture as well. But it still remains one of the best performing algorithms. So that was a listwise approach. There are other techniques that are based on this listwise technique of looking at into the entire ranking and optimizing for the entire ranking. And there are several approaches that have been proposed for that. And most of these approaches are based on using the Plackett-Luce model to first compute a probability of generating a particular rank list of results given the scores generated by your system, and computing how that probability distribution over the ranked lists differ from actual probability distribution or actual rank list that you should have observed given the relevance labels that you have. So what do I mean by that? Let's say you have a bunch of documents, D1, D2, D3, blah, 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 and the first part in here is to generate a distribution of over all possible rankings that you could generate for when you were to rank these documents. So you would have one probability value for like ranking D1, D2, D3, D4, another probability value for D2, D1, D4, D3, D4, and so on. So all possible ways. So in here again, instead of like probability of document I being ranked over document J, you are generating a probability value for an entire ranking and distribution over rankings. And how do we do that? Basically, you use the Plackett-Luce model to generate this probability distribution, which says if a document so this SI corresponds to score for document I. So this is score for document 2, for example. So for to compute this distribution, we have to compute the probability of generating each possible ranking, right? Let's assume that we are trying to compute the probability of generating this particular ranking, where D2 is ranked above D1, which is ranked above D4, and D4 is ranked above D3. So according to Plackett-Luce model, this probability can be computed by phi of S2 divided by phi of S1 plus S2 plus S3 plus S4. Basically, what this measures is, given the score of all of these documents, what is the probability that S2 would beat, or document 2 would beat all the other documents? So again, it goes to the top rank. Okay, so now the top slot is taken by S2. Now I have to rank the rest of the documents. Then in this one, D1 has to go top. What is the probability that D1 wins over all the rest of the remaining documents, which is D1, D3, and D4? So now D1 is gone. Now what is the probability that D4 wins over D3? And finally, we have D3 is left. Okay? So this is the probability of generating this particular ranking given the documents that we have. Okay? Okay, and you can compute this probability over all possible rankings. So at the end, you have a probability distribution over all the different rankings that could be generated, given the scores that are generated by your system. Which is, and this value is actually based on, this probability computation is based on this Plackett-Luce model, which is commonly used in generating this probability distribution over rankings. Okay, so in here, phi can be a transformation, like it could be linear, exponential, or sigmoid. A commonly used one is sigmoid in this case. And then given this probability distribution over rankings, there are different approaches of doing the optimization at the end or computing the loss function. One could be that, so now you have, given the scores, you have a probability distribution of rankings. Then you can generate the same thing given your relevance labels. And your objective function could be the KL divergence between the rankings obtained using relevance labels and the probability distribution that you have obtained given your scores. Okay, so that was ListNet. That was proposed in 2007. And it seems to be also doing quite well. Actually, one challenge in these approaches is obviously you have to kind of generate all possible permutations of the ranking of all of these items. You have to compute the distribution over all possible ways these items can be ranked. So they are not very efficient.
Is that a problem? Is the fact that the KL divergence is not symmetric, is that a problem?
Not really. I mean, in a sense, that's a problem. That could be a problem in all the machine learning algorithms, right? Because you assume that there is an actual distribution and there is an estimated distribution. The way KL divergence is defined is that there is an actual distribution.
Of course. I was just wondering why they don't use the JS divergence.
Janssen-Shannon divergence is also used, actually. But this one is used because it's relatively easy to optimize, and I don't think they differ that much. So for those who don't know, Janssen-Shannon divergence, KL divergence is not a symmetric metric. And what does it mean? If you start from one distribution, if you compute KL divergence between P, starting from P to Q, it's not the same as computing the KL divergence between starting from Q to P. So it matters where you start from. And that's not actually a metric by the definition of what a metric is. KL divergence is not a metric because by definition, a metric has to be symmetric. So in that regard, KL divergence itself is not considered a metric. And what people have come up with is an alternative to that, which is called Janssen-Shannon divergence, which is basically the average of KL divergence between P, given P to Q, plus given Q to P and the average of that. So now in that case, it becomes symmetric. But in optimization, it doesn't really make that much of a difference, and that's why people still use KL divergence. Okay, then the other approach that people have come up with to kind of solve this is potentially to use another objective function, which is given these distributions, instead of computing KL divergence between the ideal lists generated and the one given the scores, you could also compute what is the probability that, given these scores, you could generate this ideal ranking that you could generate given the relevance labels. So given the relevance labels, you produce one ideal ranking, which is like a ranking where relevant items are ranked above non-relevant ones. And you compute, given these scores, what is the probability that you could have generated this particular ranking and optimize for that. So that's another approach, slightly more efficient, and seems to be working quite well as well. And yeah.
How do we deal with the documents that have the same relevance? We need to have the actual.
So in this one, for example, that's true. You could have several rankings, actually. And in this one, people tend to use like a max or average of all possible ways that the probability of generating any of these possible rankings. So another way of using these approaches is based on having list-wise objective metrics. Smoother objective metrics. Previously, what we were doing was given scores, we were first trying to generate some ranking, and each document was assigned to a particular rank. And based on that, we were trying to compute these probability distributions or computing delta and DCG and so on. Another way of doing it could be, instead of having assigning a document to a particular rank, we could kind of compute a smoother version of it, where each document is assigned to some rank that doesn't necessarily be even have to be like an exact value. So it could be a distribution over ranks, which is soft rank, which I won't talk about now, or it could be some smooth rank value. So what this one does is, instead of having a specific rank points, discrete ranks, you could have like real values for ranks, for example, and then you could try to optimize for that. So now that becomes a little easier to optimize for, because you are not exactly doing this discrete kind of sorting step. And that's smooth DCG. And the way it works is, for each document I, you kind of compare your document I with all the rest of the documents. And you compute the probability that this document I would beat document J, and which is this value here, G alpha. And based on that, you assign document I an expected rank. Okay? And in this particular case, this G alpha was defined by this sigmoid function. And now you have some real valued ranks. And now you can optimize for these real valued ranks, the final objective that you have. Okay? This overcomes this problem of having non-smooth metrics by this hack of way of coming up with real valued ranks, and it also seems to be doing quite well. Yet among all these algorithms, like I said, lambda rank is still probably one of the most preferred one, and lots of algorithms are kind of based on variants or extensions of some of the ideas that lambda rank is based on. Okay, this is the end of the learning to rank part of the lecture. Any questions? Okay, if not, Pascal will take over. Thank you.
Can everybody hear me? Perfect. Thanks, Emine. So I want to make a point that I think the sections that Nick and Emine covered today are really the important fundamentals that if there's one, well, if there are two things that you should be taking away is kind of these fundamental understanding of what these loss functions are, or the fundamentals of neural networks. But having said that, we are actually at a very interesting phase in IR today, especially for people who are interested in machine learning for IR, where we are seeing some pretty significant moves in models in terms of metrics and performance that's been caused by these deep learning and the introduction of these kind of deep learning based models in IR. So my goal for the next hour would be to maybe not be able to cover all the details of these models, because again, deep learning for IR is a very big area, but to leave you guys with enough breadcrumbs to kind of motivate people here in this room to actually get interested in this space, and then go follow up and leave you enough pointers so that you guys can follow up and go through more of the details. So one of the things, I just said that there's a lot of interesting things that's happening. So what do I mean by that, right? So this is my kind of two plots, the story of like the state of neural IR today in two plots today. So this is, I think the plot on the right is actually more interesting, but we'll get to that one. So this is something I actually started doing, I think, back in 2016, I think is when I first drew this, or maybe this was 2017. I think Chris Manning gave a talk at one of the keynotes at SIG-IR, if I'm not mistaken, at 2016, where he kind of made this comment that next year, neural models, deep learning models are going to take over SIG-IR, which got a lot of people talking about it, both for and against. And it was at that point that I kind of started manually tracking, going through SIG-IR proceedings and looking at full papers and counting how many papers were about what I would consider as like deep learning models. Yeah, and this has actually been pretty significant, and I've kind of continued doing that. And honestly, if you had asked me, I wouldn't have expected this kind of a growth. So we'll see what 2020 looks like here. Not all of this is web search. So for example, last year, I noticed a lot of the deep learning papers were about recommender systems and graph-based algorithms and so on. So yeah, there's a lot of diversity again within this thing. But probably more interestingly, there actually has been a question for a while on, there's a lot of papers on deep learning that people are writing, but are these models really working in practice? There has been some questions about, are these models really being benchmarked correctly with traditional models and so on. So one of the things that, again, the four of us, the same four people who are doing the lectures and labs today, we've been also been for a while trying to work on some data set and benchmarks for these, on which you can try these deep learning models for IR. We've gone through a few phases with MS Marco and the leaderboard and so on, but it's kind of culminated into this in last track with having a deep learning track. And this is just a kind of a pictorial. So by the way, the track overview paper is still technically not out there. It's being held back because, again, people write cigar papers. So the overview paper will come out in, I don't know, in a few weeks or so. But this is like a kind of an anonymized, without giving away anything about specific runs. This is kind of just showing what kind of performance we got from the different runs. And what we did is we manually classified the runs in 3 different groups, completely traditional IR models, anything that's pre-deep learning kind of approaches. And then within the deep learning, we kind of broke it up into BERT-based models or BERT-style-based models. So there was like one XLNet in there, and then everything else that's deep learning. So that's basically the BERT-based model is what is just like, we have an acronym NNLM, like neural net language model, and then NN runs are the other deep learning models, and then this is the traditional runs. And basically the gap is like the best performing from each group. What is the kind of performance differences that we are seeing? And this is like a pretty significant jump. Like for IR, we are all very used to tweaking our models and things till we get like a little jump in our performance. And this is like a pretty significant bump, right? So that's my kind of motivation for everything that I'm going to be talking about for the next hour, or on why anybody should be paying attention for the things that I'm going to talk about for the next hour. So what's missing in learning to rank and traditional methods that deep learning is kind of focused on? Or rather, what is that part that deep learning is really emphasizing on that may not have been as much emphasized previously? So I think the main topic, the main answer to that, my personal answer would be that a lot of the deep learning work is really strongly focused on learning good representations of text for matching. So what do I mean by that, right? So we've all heard through this week about BM25, term frequency-based, TF-IDF style models. So you get a passage, or you have a collection of passages or documents, and you have a query like Albuquerque. You go to your document and see how often the term appears, how often the term appears in the collection. Based on these things, you decide how relevant this document might be to the particular query. So here's an example of a couple of passages where both the passages have exactly one occurrence of the query term, right? So if you think of BM25 or TF-IDF, and then they're pretty much similar length as well. So they would have a very similar kind of a score from any of these term matching model. So now if we looked at these two passages, by the way, the passage on the left is I think the beginning passage from the Wikipedia page on Albuquerque, whereas the second passage is a passage from Wikipedia page on Microsoft talking about Microsoft starting in Albuquerque. So if we look at these passages, we actually quickly spot a few clues that tells us that the left passage is about Albuquerque, whereas the right passage is not. Because the left passage talks about city, altitude, city population, metropolitan area. So the moment, even if you could not read this whole passage, if I just told you that this passage has these words that you would typically consider to occur in a passage that describes a city, then it already, you're kind of like, yeah, that's probably about a city, and and given that the word Albuquerque appears in there, it's probably relevant to the topic. It is on the topic Albuquerque. Whereas if you look at the second passage, you see words like basic interpreter, simulator, and what else? MITS, and so on, Altair. So you kind of immediately have a reaction that, oh, this sounds like something about a tech topic. This doesn't seem to be about a city, right? And this is effectively one of the motivation of thinking about learning text representation is that if you are able to learn a good latent representation of what this passage is about, then you would know that this passage is probably more relevant for a query about a city than potentially that passage that seems to be on a tech topic, right? So a lot of the deep learning stuff is really focusing on garnering evidence of relevance by looking at non-query terms in the document. And again, it's not like this is the first time deep learning is the first time we've seen this. We've seen this in LSI and all of those other models before. We've seen this in query expansion and PRF. There are different approaches. Deep learning is taking a slightly different approach at this and trying to take a stab at the same problem. So now I want to just, in this slide, I want to kind of connect it back to some of the things that you've heard in Amin's lecture, right? So in Amin's lecture, we talked about, we have a neural model. The input to the neural model is a feature vector that's conditioned on the query and the document. It's conditioned on the query and the document. So now imagine a very simple kind of a overall skeleton for a deep learning model would be where I have the same query in the document, but instead of creating a vector of handcrafted or hand-designed features, I just want to give the model the query text. I want to give the model the document text, and the model should do its thing and just tell me how relevant they are. So for example, here's a very simple kind of, as I said, a skeleton model, which kind of corresponds to one of these more earlier models that was quite effective and quite popular, which is called DSSM. Funnily enough, the acronym for DSSM, or rather the expansion has, they've kind of changed it over multiple papers they've written, but that's fine. So we're just going to refer to this as DSSM. So it would have this kind of a very typical structure where you have, this is the query text, this is the document text, or passage text or whatever, and you're inputting both to some model, and that model outputs a representation of the query and the document in the form of some kind of a dense vector representation or an embedding. Right? And then given these two dense vector representations, you can compute some similarity measure between the query and the document. So a simple thing could be cosine similarity or a dot product. And your goal is that given a query, a relevant document, and a non-relevant document, the vector representation of the relevant document should be more similar to the query than the vector representation of the non-relevant document to the query vector. Right? So that's the kind of the basic idea. And we're going to go through about step by step about what does it even mean to input, for example, text into a model. Like how do you input text into a model? What does it mean? What kind of loss functions would you use here, and so on. By the way, a lot of the, like, on the topic of like what kind of loss function would you use and so on, that part is actually not different than what, for example, Emine talked about in feature-based learning to rank. It's just that really the input to these models have now being, instead of numerical feature vectors, is now raw text, and you actually want to learn representations on top of raw text. But the other learning to rank framework, loss functions, all of those pretty much translates exactly to the discussions in this section. Okay. So let's start with this question. How can we input text into a neural model? And the short answer is there is no one answer, obviously. So I'm going to go through a few different ways we can think about converting text into a form that, that we can run a neural model or any machine learning model on top of, right? So I don't know if we've already mentioned one-hot encoding, but just for I'm going to take a quick aside and just define that. So let's say you have n different items, and I'm going to talk in very generic terms, these n things could be anything. N could be words, n could be different entities, or n could be different like alphabets or whatever. So let's say you have n different entities. One way you can represent these n things is by a sparse vector, where the vector is exactly of length n, and it's 0 everywhere, except for the position that corresponds to the item that you're trying to represent. So let's say you had 3 entities, a dog and a cat and a horse, and that's all your universe of entities was. Then you would represent either of these things by a vector of length 3. So let's say the first position corresponds to dog. So for dog, you would write the vector as 1, 0, 0. For cat, it might be 0, 1, 0, and for horse might be 0, 0, 1, right? So that's what I mean by one-hot encoding. It's a binary vector with just 1, 1, and everything 0. So now let's come back to our original question. So let's say we have these very wise statement. For anybody who's a dog lover or cat lover in the audience, it's a piece of fact. Dogs have owners and cats have staff. So let's say you have this piece of string and you want to encode it in a way that you can then feed it to a neural model or some other machine learning model. So one obvious thing you could do is so you could say that I have, let's consider I only care about English characters in this particular scenario, plus let's say numerals. So and the space separator. So that means I have 26 characters, I have 10 numeric characters, and then 1 space. So I could come up with a one-hot representation where each vector is of length 37, and then each position corresponds to either an English alphabet or the numeric or a numeral or the space character, right? So I can represent each character by one-hot encoding the character with a size of length 37, which, by the way, I'm just going to call as channels here, as the 37 being the number of channels in this case. So we can represent each of these characters with a one-hot encoding, and then to represent the whole string, you can do a couple of different things at least. So one is, let's say I'm going to represent the whole string as a bag of characters, in which case what you could do is you could take all of these one-hot encoding vectors and just sum them up. So that just means that now you end up with a vector that's, again, of length 37, and then at each position, it's the count of how many times this character appears in the whole string. The other thing you could do is you could take these vectors and you could concatenate them, right? So now you end up with, let's say if you have a string of length, I don't know how many characters, I'm not going to count it. Let's say I have a string of length 20, then I would actually end up with 20 multiplied by 37 length vector. Right, so I'm just concatenating those one-hot encoding vectors. The benefit of doing that is, in this case, you are actually keeping the sequence information intact. So the model that run on top, it could take advantage of the fact that you know what sequence these characters appeared, rather than in the bag of characters approach. So there's like a couple of ways, even within this diagram, that you could get representation for text. The next thing you could do is, it's kind of very similar to the previous idea. So you're still mapping each character into a one-hot encoding vector, but you know the concept of words. So there's no reason for the model to really treat every string as a sequence of characters. It could treat every string as a sequence of words. Like, it doesn't need to really learn the meaning, the concept of words, because we know it's easy to point out to the model. Let's make the model's life a little easier, right? So what you do here is that for each word, I'm going to represent the characters by a one-hot encoding for each of the characters, and then for each word, I'm going to sum these words up. So I end up with a vector, a sparse vector, where each position is the count of the number of times the character appears in the word, but I have one of these vectors for each of the words that I have. Right? And then I can take these vectors and I can concatenate. So now it's going to be, so in this case I have 6 words, and let's say my one-hot encoding vector was of size 37. So now I end up with the final representation as 6 multiplied by 37. That's the length of the final vector that I end up with. And I keep saying we'll end up with a vector of size 6 by 37. That's not exactly true. Like, you wouldn't actually think of it as one long vector. You would actually think of it as a tensor. Like, you would actually have a tensor where one dimension length is 6, the other dimension is 37, because that's how you are going to interpret it, right? That's what is interesting in here. So this is another way we can do this. Let's take another step forward. Instead of doing characters, each character getting a one-hot encoding, what if I took n graphs? So for example, in this case, I'm specifically looking at trigraphs, right? So I'm going to basically, in my one-hot encoding vector, now each position corresponds to a possible character trigraph in my corpus. And just for some multitude of reasons, I'm just going to mark the beginning and ending of the words with a hash character. So for this word, I would basically say the character trigraphs are hash DO, DOG, OGS, and GS hash, or GS sharp, depending on, I think that's American versus British way of saying it. Anyways, so now this vector length is going to be much bigger. It's going to be the all possible character trigraphs that you can have in your corpus. Question? Yeah, no, go for it. So the hash character is basically just trying to denote the beginning and the ending of the words. Why am I counting? Sorry, what?
You say, so you give an example of like hash, G, and O as being a part of
Right.
the three. Why don't you count the hash? What's the significance of
So the hash is, so basically it's just saying that I have a word which starts with DO. And the way you denote that is you basically have a position which is in the one-hot encoding as hash DO. So all the positions which corresponds to hash and two other characters, it means those two characters appeared at the beginning of the word. So so it's basically, I'm not actually sure how much it matters to not have that hash. Like I haven't run that experiment or don't remember an exact evaluation of it, but it actually came from the DSSM paper. That's what they did. But yeah, I mean, it's completely valid to not do the hash and do this everything else exactly same. I don't know how much it would matter performance-wise, but probably has some effect. So what I was going to say is, so now the length of this one-hot encoding is all possible character trigraphs in your corpus. Typically, if you do it for like, again, 26 English alphabet plus space plus 10 numerals, I think it's something around 56,000 something. What people generally do is, again, all of those character trigraphs, there are a lot of character trigraphs that never appears in your corpus. So they generally say, I'm only going to look at the, let's say, 30,000 most popular character trigraphs. They will have a representation here. Any other character trigraphs that appears in my input, I'm just going to ignore it. And hopefully everything goes okay. So yeah, so you do this for, again, you're still doing this for words. So you end up with one vector per word. And then at the end, you could concatenate those word vectors, or you could even sum them up if that's what you wanted to do. So this is another just kind of moving on to character trigraphs. By the way, there's also been work that instead of having a fixed trigraph, they've actually done like n graphs where n goes from 1 to some other value. So you might consider single characters, 2 characters, 3 characters, and so on. If anybody's interested, we can talk about why people do that. Actually, we did it in one of the earlier papers because I'm not going to go into it. We can talk about it if anybody's interested, but I'm just saying that it doesn't have to be a fixed n. Sometimes it is n where it's like in the range of 1 to 3 or whatever. And last but not the least, this is actually quite common, which is why not just make one-hot encoding for words themselves? Like forget about characters altogether. So I'm just going to look at the most popular words in my corpus, or maybe the most important words in my corpus. Maybe I remove stop words or words that are too frequent in some ways. And then for the other words, I'm just going to pick the 50,000 most popular or most important words, and those are the only words I care about. I'm going to ignore everything else, and I'm going to give a position in the one-hot encoding to each of the words themselves, so that the model doesn't need to really care about going from characters to words. Like in the other case, you could have 2 words which share a bunch of trigraphs, but their meaning could be very different. The model needs to learn that these are actually different words. Where here you're like, nope, they're completely different words. Of course, this also is a problem where there might be words that actually share most of the trigraphs, but that's because these 2 words are actually related with some different prefix, or like I add an ing or I add an s at the end or so on. The other model might be able to pick up on that and based on the scenario, whereas here those will be 2 completely different words and the model has no idea that there is any relationship between them. I mean, it might infer some things, but it has to infer. There's no reason for it to translate anything it learns for one word to the other. So now we know we have a way to feed in this text into model F1, model F2. By the way, coincidentally, the first DSSM model was basically a bag of character trigraphs over the whole string. And then the model themselves were just simple feed-forward networks, right? So it just took a vector of length, I don't know, 30,000, and then with basically each position, the count of how many times this trigraph appears in the string, put to feed-forward deep network. Each of them produce a vector output, a dense vector output, which is considered as the representation of the query and the representation of the document. You do cosine similarity on the top, and that's your score. Now, this is no different from the neural models that Emine talked about, where you give it a feature vector conditioned on query document, and the model produces a score, right? So let's look at that abstraction that I have some neural model. It took different kinds of inputs, but they both produced a score for a query document pair. So the rest of the machinery, where we are talking about the loss function, we are talking about how to train this model, doesn't need to be any different. And this is exactly what happens in this case. So for example, you can train this with the RankNet loss function that Emine talked about, where you take a query, a positive document, negative document, get query, positive document score, query, negative document score, and then given these two scores, you just do cross entropy with softmax, right? And that's basically what RankNet is, and that's, again, typically what people do for DSSM. In fact, what they actually do most commonly for DSSM is the generalized cross-entropy loss, where they would compare one positive document with, let's say, 9 other negative documents. So what you're doing is this is exactly the same thing as the RankNet loss we saw before. So this is the score of the query document score for the positive document, and then in the softmax inside, this is summing over the positive document and all the, let's say, 9 different negative documents, right? And here, in just that, in this case, in the deep learning case, it's not that the model output a single score, it actually output a query document vector, but you did an extra operation and did a cosine similarity and landed up with a single score again. So it's not really that different. So that gives us at least some basis. I'm going to quickly check if anybody has any questions so far before I move forward. No? Because everything's clear, or I've lost everybody already? No, hopefully not. Yes, go for it. I'm also asking you people to ask questions so that I get an excuse to drink water. So.
So here you started with a query and right?
Mm-hmm. Yeah, yeah.
Then in the loss function, you are using D plus and capital minus.
Yes. So sorry, some of the slides I might have made it like a couple of day before yesterday. So this is like a screenshot from a different paper, and this is from a different one. So what's actually happening here is, imagine this is Q and this is D plus. And now imagine you have similarly parallel here a D minus. Right? So what you would end up doing is you run the exact same document model on D minus as well. So you get a vector corresponding to that. And then you do a cosine similarity between the embedding of the query with the embedding of the positive document. But you also do a cosine similarity between the embedding of the query and the embedding of the negative document. So then you get 2 different scores. Right? So that which corresponds to cosine QD plus, and then you get here cosine QD plus and cosine QD minus.
You do that for every labeled document that you have.
Yeah, so here basically this is, so by the way, this is where I think this classification or taxonomy of pointwise, pairwise, listwise kind of falls in. Pairwise, so pairwise, let's call it pairwise plus plus. I'm just going to make this up. But pairwise assumes you are comparing a positive document with a negative document. But you can imagine comparing a positive document with k negative documents. But they're not necessarily, you're not considering the gradedness between the negative documents. So here in this case, for example, you might pick the positive document might be an excellent, and the other 4 are just all bads, or all random negatives that you sampled from your collection.
So this kind of list-wise.
It's not listwise, because what listwise is really going for is to optimize by considering the position bias, right? So this is
Still binary inference.
Yeah, so this is listwise if your retrieval scenario was specifically about ranking 5 things where 1 is positive and the other 4 are negative. And even then, it's not really considering the position discounting, the fact that switching between whether the positive document is the best versus second best, and second best versus third best. In this case, it doesn't have that. It's not. It doesn't map to any user model of position discount and so on. So it's actually closer to, I would say, pairwise, except that you're considering not one negative but multiple negatives. And by the way, again, this is true for even normal feature-based learning to rank as well. Like you could do the same thing there as well. It's not specific to deep learning. Okay, so I'm going to move to a slightly different set of a slightly different topic, which is kind of introduce a few different common architectures in deep learning, right? And I'm taking an example of an image. I wanted to take an example of text, but I ran out of time in putting that in. So, but let's go with image because I like visual things. So let's say you had an object recognition problem, right? So you had a model that takes a picture and tells you if there are birds or how many birds are there in the image. So one way you could input this image, you could just take the pixel values at each position, and then you know the x and the y. So there's like, almost think of the input as like a three-dimensional tensor with height, width, and then the number of channels being 3, which is the pixel values, RGB values. Now, now you could actually run a fully connected network on top of this tensor, right? And there's nothing wrong with it. But if you think about it, one of the things is that, so let's say I had a function that learns to detect a bird. The function should ideally be the same if I apply it here versus if I apply it here versus if I apply it here and so on, right? But when you take this whole picture, serialize it into a big vector and give it to a fully connected network, what is effectively happening is that the model that looks at this portion of the image isn't looking at a different part of the image, right? So you're basically trying to learn the same logic over and over at every position in the picture, which makes no sense, right? So what ideally you would want to do is learn a function that learns to detect a bird and then apply it all over the image repetitively. So this is, will lead us to ideas of convolution and others, but in general, it will lead us to this idea of shift invariant operations. So basically the idea is that I'm going to learn something that I'm actually going to apply over different position of the input, so that I don't have to learn the same thing over and over. So for example, if you think about text, let's say I give you a sequence of words, and you're going to learn, let's say, word embedding. So first you get the embedding for each of the words, and then you learn some function on top. But if you're going to learn a word for, if you're going to learn an embedding for the word university, it doesn't matter if the word it doesn't matter as much if the word university appears at position 1 or at position 10. You would imagine that the embedding should be pretty similar in both cases. There's some contextual information that you can use, in which case it could be different, but let's not go into that. But if you were to naively take in whatever the things we've talked about before and just train a full, like in terms of inputting, how to input text into neural models, and then just naively put a fully connected network on top, that model would end up trying to learn the word embedding here and the word embedding here completely from scratch, independent of each other. If the input is a sequence, not if the input is a bag of words. But we'll come to that. So this will lead us to a bunch of architectures, and in all of these cases, I'm going to actually try and talk about them in a visual way because we basically don't have enough time to like really work through all of the maths. But if you guys can get the intuition, these are actually really, really simple. If you get the intuition, the visual intuition, I think then the math just follows. It's actually really simple. So what I'm doing here is, in this example, so this is my input sequence. I'm taking a few shortcuts. So consider that each of these squares corresponds to a single word, and then the word itself could be represented by a vector, but then I'm not showing that dimension. So imagine there is a depth dimension to this text, right? And for string, it's obviously a linear, it's a sequence, so I just have one dimension, so this is like representing whatever, 15, 20 words or something. So now what I can do is I can take a window. So basically I'm gonna learn how to, how to represent sequences of 3 words, right? So I'm learning a function, f, to represent sequence of 3 words. And the way I do it is I apply the function on the first 3 words, and it gives me a vector output. I apply, and then I move the window by position position, and I learn a function. Actually, here it moves by 2 positions, and it applies the same function on these 3 words, and then I apply it to these 3 words, so on and so forth. It's exactly the same function with the same tied parameters, shared parameters, as I apply it across the window. And each of these produces some vector, and then I do something on top, right? So what happens here is that when the gradients flow back in this model, it affects the same function, whether it was applied here or here or here and whatnot. So let's say I had the same 3 word here and the same 3 word here. It would actually get the gradient and it would flow back to the model both when it was applied here or versus when it was applied here. So this kind of goes back to the previous diagram where we're trying to detect birds, but here it could be something else. Now, I did not say what this function f was. And technically, this function f could be anything. But then generally, depending on what that f is, you get a few different very popular kind of architectures. So if f itself is some kind of a linear function, by linear I mean like in the notion of linear layer. So you could have something like, well, not linear, it's like fully connected, let's say, sorry. So let's say it's some kind of a sigmoid. So let's just say this is sigmoid or tan h of wx plus b, where x, by the way, is these 3 things together. So if you do something, if the function f looks something like this, then you typically call it a convolution. Right? So convolution is basically doing what you would do in a fully connected network, but instead of applying it on the whole input, it applies it in a window and moves the window all over, and then you get the output in the next layer. I feel like you have a question. No? Okay, sorry. However, by the way, notice the picture did not change, even though I changed the slide. Right? And that's because pooling is very closely related to convolution, except that in pooling, what you actually end up doing, so remember that I have this length dimension and then I have the depth dimension. So pooling, what it basically does is it will take this, I don't know, length by depth vector, and typically produce a vector that's 1 by depth. I'm going to give an example because honestly, these definitions could be a little fuzzy because there's so many different ways of doing pooling that maybe my definition wouldn't align to all of them. So I'm going to take 1 or 2 very common pooling strategies and just describe those here. So one thing you could do is you could take each of these vectors at this position and then average them, so that you end up with 1 vector with the same depth. So you're averaging, let's say, the first channel across this whole string. And then you're averaging the second channel across this whole length. Eventually, if the depth here was, say, 10, you end up with a vector that's 10, just a vector of length 10. Right? So that's what you would call average pooling. If instead of averaging you did sum, it would be sum pooling. If instead of average or sum, if you did max, what do I mean by max? So again, you have 10 channels. For the first channel, I'm going to take the max value across this. For the second one, I'm going to take the max value across this. Again, I end up with a vector of size 10, but in this case, we call it max pooling. So there are all of these different pooling strategies that you can use. The one interesting thing that people do is they typically combine convolution and pooling. And specifically, one thing that is kind of common, especially for text, is where they would do a convolution. So you get up all these vectors, and then they do a global pooling. So global pooling is nothing but where the pooling is not being applied by window. It's actually being applied to the whole sequence. And one of the reasons this is quite useful is notice that at this point, my sequence can be different length, right? For different inputs, the sequence length could be different. But if I do a global pooling, I end up with a vector of a very fixed dimension. So anything that comes above this can assume that after this layer, I have 1 by whatever the number of channels is. That's the output at this stage, and then the upper model can assume that. Whereas if in previous 2 slides, they were actually generating an output, which is a function of how long the sequence is, right? How are we doing on time? Okay, we're pretty good. So in the previous 2 cases, so for example, for a short string, I would have, let's say, 3 of these. For a long string, I could have a much larger. So you need to handle in the neural network, how do I deal with an output that's actually variable length, right? So, and one of the ways you deal with variable length is put a global pooling, and then you don't have variable length anymore. So that's one of the tricks. Last but not the least, And there is by the way, for people who are actually familiar with convolution, recurrence, and other things, you will notice that I'm actually drawing these diagrams slightly differently, and it's kind of intentional. I'm kind of intentionally drawing convolution and recurrence to look exactly as close as possible, because they are very related. Like, I want to emphasize the similarity rather than the difference between these different things. So in recurrence, what you end up doing is you actually, so in the convolution case, what happened is, so let's say when I projected these three words into a vector, I did that completely independently of these three words that got projected here. And right? They have no connection between themselves. But you think of that, let's say if I'm going to look at a string, there seems to be some sequential dependency. So let's say if I say University of Cape Town, for town, it matters that it came after Cape, right? Rather than town if it came in some other context. So one of the things you might want to capture is some kind of sequential dependency, and this is where recurrence comes in. And so what happens here is this looks exactly like the convolution case, except that the function f that you're applying to this input in the window, it also takes in another input argument, which is the hidden state from the left-hand side, which for the first case is empty. It's just zeros or whatever. But for any arbitrary other position, the function f is now a function of what's in the window, but also the hidden state to the left. So that's effectively is what the only difference for is in the case of recurrence. Now again, you can get into more complicated things. So you can get bidirectional RNNs. You can get I don't know. There's multiple variations where it might also take a dependency on not just the left but also on the right, and so on and so forth. By the way, notice that the hidden state here is effectively a function of everything in this sequence that has come before. Right? So there is some, generally people would associate a special semantics to the last hidden state, which seems as if it is capturing the information across the whole input sequence. So that's typically what you would do with single RNNs. Yeah, you would just take the output at the very last, but there are many variations. Again, I'm not going to go through all of that because we just simply don't have the time to cover those topics in that much details today. But again, if you guys want to talk about it, I'm happy to talk about that after this lecture. We might even have some time during the lab sessions to chat about this if anyone's interested. I'm just wanted to show, like, so we talked about the DSSM model and we talked about convolution recurrence. So there is some obvious papers to be written there which have been written, which is take DSSM, add convolution instead, so it becomes convolutional DSSM. There's also a paper that does recurrent DSSM. There's a paper that does recursive DSSM. We're not going to go in that. But this is what it looks like. So for the DSSM model where we took the text, everybody remember what I'm talking about in DSSM. I'm talking about this thing. Right, so we talked about this. Here the text came in. This was a fully connected network. Now I want to make it a convolution network. So what happens is this. So now I have a text like this, auto body repair cost calculation software. Actually, let me do that in that example. So you have online auto body, so you look at 3 words at a time. The convolution window is of size 3. So each 3-word sequence or window gets projected into a hidden layer. And by the way, the S and there are 2 start and strings, start and string end markers. So that's the S in angular brackets. So you have S online auto gets projected to something, online auto body gets projected separately, and then auto body S gets projected separately. But each of these are getting projected by the same function f with shared parameters. Right, you're applying the same thing over and over, so convolution. So then you get that, and then they do a global max pooling. So that gives you a fixed vector of length 300. 300 is just the hidden layer dimension here. And then they have some more fully connected network and eventually end up with a single vector of length 128 for the query. Same thing for document, cosine similarity, rank net loss function, and voila. So, and this is where I think this is important, is to think about all of these different concepts separately, and then you put the Lego pieces together, right? So we've learned about loss functions. Any loss function can be applied independent of other things. We've learned of different input text mechanisms. We are learning about different architectures like convolution, recurrent layers. You can mix and match all of these things and get different kinds of properties and different kinds of performance. The other thing, so we are here obviously not talking about neural networks in general or deep learning in general. We are particularly, or not even neural deep learning for text in general. We're kind of focused on deep learning for IR, or yeah, so we're talking about deep learning for IR, or even specifically deep learning for search. So the typical problem for us is we are given a query and a document, or a query and a passage, or a question and an answer, and we're trying to match those two things. And we're trying to estimate how relevant is one given the other, right? And we saw one model where you learn vectors of those two, and then you just do cosine similarity. Another approach is you take the query. So here, every circle is a word, and you take the document. Again, every circle is a word, and you just project each of the individual words separately. Or this could be a convolution. This could actually be, I'm projecting 3 words at a time, but whatever. But you're not coming up with a single representation of query and document. Instead, you're coming up with either a representation of each word of the query and each word of the document, or each window over the query or each window over the document. And then what you do is you basically create this thing, this interaction matrix, where, for example, let's stick with the example where we are representing each word as a vector in the query and the document. Then this is some function of, actually this diagram is based on convolution, so let's stick to that. So it's actually moving 3 windows at a time. So this is a function of the representation of these 3 query words and these 3 document words, right? So now you get this interaction matrix where, for example, this one would be the representation. It would depend on the how well these 3 words in the query match with those 3 words in the document, right? So this notion of interaction matrix, it's basically query length by document length, and then each position either compares a word from the query and a word from the document, or a window over the query and a window over the document. And this has some interesting properties, and we'll look at that pretty soon. I'm actually going to wait till I get to a different example to kind of visually show what ends up happening, to give a bit more intuition about why this even makes sense. And then you have this interaction matrix. And by the way, there could be, again, a channel here, depth to this interaction matrix. And then you could even have some other machinery, neural machinery on top. It could be a fully connected network. In the simplest case, it could be a convolution, 2D convolution moving over this space, and so on and so forth, right? To basically summarize and give you the final estimate of relevance. So how do you, actually, so one thing that we talked about here, so let's say, again, I'm just going to, for simplification, assume that this one compares just the vector of this word and the vector of the last word. So you, just like in DSSM, well, not like DSSM, you don't have query and document embedding. You have the embedding for one query word and one document word. But given these 2 vectors, one thing you can do is you can just do cosine similarity, and you get one number, right? You could do element-wise product. So let's say if these 2 vectors were both of length 10, then you again end up with a vector of length 10, where each element is like the output value at position I is the product of the input value at position I of the query word and the document word. You're just doing a product of those 2 things. But there is, what you really think of is, so let's go with the cosine similarity case. So let's say you do a cosine similarity, and you get a real valued number, right? So this is a continuous number that tells you how similar this query word is to this document word. One of the interesting trick that was proposed by the kernel pooling paper that we are going to look at here is basically it looks at that I'm going to do similarity, let's say something like cosine similarity, but instead of keeping a single real valued number, I'm actually going to transform that into, let's say, 10 features, where each feature triggers, becomes 1 or gets close to 1 if the similarity is in a certain range. So I have one feature that tells me if the similarity is very close to 1. One feature that tells me if the similarity is very close to 0. One feature tells me that if the similarity is somewhere between 0.2 and 0.3, and so on and so forth, right? So that's the idea behind kernel pooling. And the trick is really simple. What they do is they take the similarity score between the ith query term and the jth document term, and then and they basically want to detect these 10 features. And one of the features, let's say it says the similarity is somewhere around 0.3, right? So what they would do is they will take the similarity score minus 0.3 whole square divided by, this is actually a constant. It looks like standard deviation, it's not. It's a constant here. And it basically, what this RBF kernel is doing is that it will actually have a value very close to 1 if the similarity is very close to 0.3. And it will basically get close to 0 the further you are away from 0.3, either on this side or the other side. So it's a very interesting, nice trick to basically go from a single real valued number to almost like 10, 20, 30, whatever. Depends on how many ranges you want to consider. So you can have these, let's say, 25 different features where any one of them triggers if the similarity is in a particular range. So that's the key trick in kernel pooling. Then they have a couple of other things, which is actually goes back to some of the intuition from something like BM25 and others. Even in the duet work that we had done, a model that Nick and I with Fernando had done, we have the same intuition, which is typically what you would do is you kind of sum up the relevance estimate of one query term along the whole document, and then you apply some kind of a saturation function, if you're familiar with, like anybody who's familiar with the concept of how saturation function works in BM25, there is that's what that log comes in. It's basically doing a saturation function over the document length. If you're not familiar with it, forget it, we can talk about it offline. I'm not gonna go in that details. The key thing here is that it's actually coming up with these different features given what range the similarity function is, but it also does that other thing which I thought I would mention if you're already familiar with saturation functions. So that's the kernel pooling trick. And then another trick, and this is the duet paper that I was referring to earlier. So I mentioned earlier that many of these neural models focus on learning good representation of text, but we are always in IR dealing with query terms or document terms that can be very rare, right? So whenever you're learning representation of text, you're going to learn very good representations for things that you see a lot in your training data. And you're going to do pretty poorly for things that you've never seen in your training data. My classic example used to be these two queries. Do I have that example? No, I don't. Here. So two queries. So let's say the query Pekarovich Land Company. This was an actual query in some search log. So what's special about this query? Well, Pekarovich is not a word that appears in any training data because it's a super rare word, name of an actual company, but whatever. So if you only have models that do representation learning, it's possible that these models, unless there are some other assumptions, it may not have any real understanding of what the word Pekarovich is. So it's effectively going to just do some random projection, which technically works, but we're not going to go in that. But effectively, the representation learning model might struggle to deal with queries where it has some very rare words that the model has never seen in training data. On the other hand, we know that our typical, even simple traditional IR models like BM25 actually works really well exactly when our query terms are rare in the corpus. So if you have a query with terms that only appears in a handful set of documents, which means they have very high IDF, these are the cases where typically traditional models are actually good at. So the question is like, why wouldn't you do lexical matching in these neural models as well? Why would you only do matching based on latent learned representations, right? So that's basically the same idea here. By the way, the counter example to Pekarovich Land Company was, I think, when is the Seahawks, what channel are the Seahawks game tomorrow? And if you go to the document probably does not say what channel. It probably says ESPN or Sky Sports or something. And the latent representation might learn that if what channel appears in query, then ESPN and Sky Sport in the document might mean a strong match. So that's the kind of like non-lexical match or semantic match that you might consider. So yeah, so the idea of this paper was that, hey, why not do both with neural nets? So like, let's also think about like almost like learning the BM25 aspect as well, using some neural machinery, as well as doing the representation learning part. And then the model can combine the two scores and it can have the best of both worlds. So what do we do for learning the lexical matching? So we create an interaction matrix. But unlike the previous interaction matrix, where you were comparing, so this circle was a comparison of the learned representation of this word and a learned representation of that word. In our case now, it's just going to be 0 or 1 based on whether this word is exactly the same as that word. So really simple, right? It's just a binary matrix where the I, jth value is 0, is 1 if the ith term in the query is exactly the same as the jth term in the document, and 0 otherwise. And I was waiting for this example because I wanted to kind of talk about interaction matrix a bit more, but with this very simple example because binary metrics are easy to visualize, and then we can kind of connect it back to the other case that we already talked about. So this is an interaction matrix, by the way. So here I have, say, the first example, I have 2-word query, and then I have some length of document, and then assuming all documents are of length 1,000, just ignore that part for now. And then I have a 4-word query, and I have, again, a length 1,000. Now, what you have is a vertical bar that corresponds to where the query term matches the document term, and everything else is basically, the terms don't match. So now if you look at it, you certainly almost immediately start seeing some patterns. And this is kind of connects very quickly with some of the IR intuitions we have. So what do we know? In IR, from IR, traditional IR, we know that a document is probably more relevant if the query terms appears a lot, right? So let's say here is a document. The first 2 documents there have a lot of occurrence of query terms compared to the third one. So probably it gives us a clue that the third document is not as relevant. What else can we say? We know that if all of the query terms are represented in the document, then it's more likely to be relevant, right? So for example, this one, the first word appears 4 times, or maybe there's 5 times. I can actually see the pixels here. Oh, no, it's actually 2 pixel thick. Anyways, so I see this word appear number of times here. The last word appears multiple times here. But I never see these 2 words in the document. Again, just from traditional IR, we can imagine that that document is probably not relevant because it only matches some of the concepts or some of the terms in the query, but not the others. On the other hand, we also know that phrasal n-grams, like actually matching phrasal, is important. So that's what this is. So this is basically saying I saw the word big, deal, derby, like one after another. So I can again see those patterns.
So the words in the document are actually sorted based on the position.
Yeah, exactly. So it's query and document exactly by position. So now, effectively, the point I'm trying to make, and I'm going to go a bit, okay, actually, I need to go much faster, so if you look at this, now you can imagine if my input to a neural model was this binary matrix, I can imagine running some convolution or something, some network on top that basically just learns what is a good pattern of match that tells me that these 2 things are relevant and what is not a good pattern of match. The only difference, by the way, this interaction matrix and the previous interaction matrix we saw is that each of these positions would not be a 0 or 1. It could be a number. It could even be a vector with multiple numbers, whatever. But otherwise, it's pretty similar to this idea. Okay. So that's where the code is. There's a whole lot of other architectures which we definitely won't talk about today. The last topic, and I'm going to hopefully finish this in the last 5 minutes, fingers crossed, is to talk about BERT. And the reason I wanted to talk about BERT very quickly is because remember when we saw the TREC results, there was like deep learning non-BERT models or pre-BERT models, and then BERT-based models. We saw a pretty big jump between those. So I wanted to kind of talk about it. It's been something that quite a few people have been looking at, both from academic perspective but also from industry perspective. Don't ask me why why neural researchers are obsessed with Muppets, but that's a whole different topic altogether. Why not? Anyways, so before we talk about BERT, I want to quickly introduce a few concepts or variations of concepts related to attention. So what attention is, and again, kind of bear with me in terms of thinking about this very abstractly. Really, if you get the abstract concept, the math and everything follows very easily. So the idea of attention is, I have a sequence of things. Let's say sequence, but again, you can generalize into it being a 2D or whatever. But let's go with sequence. So I have a sequence here, and I have a context. right? So the model is getting the context from somewhere, and it's getting a sequence from somewhere. Now, the attention is basically what the model is doing is conditioned on the context. The model will basically project this sequence, each position individually into some value, and then it's going to aggregate all the values across the sequence. But I will not weight the values equally. The model should learn to weight them differently, right, based on what the context is. So for example, based on this context, I might want to give a very high attention weight to the values that are coming from this region, but I might not want to give any much lower attention to the rest of the sequence, right? So for example, if this is a word, these are other words, I might want to take the average of the values across those words that are similar to my context word. That's basically the idea. So how do you do that? That's actually, the math is really simple. So what you do is for each of these position, you learn two vectors, a key vector and a value vector. The value vector is what you're aggregating, right? But at the same time, you also learn a key vector. And then for the context, you learn a Q vector. And all you do is your attention weights are a function of how similar is the key vector at this position with the query Q, with the Q vector, right? So you do a similarity. So psi here is a function of the Q vector of the context, and then the Ki for the ith position, what is the key vector. So you're basically doing a similarity between the query vector and the key vector at all the position, and then you apply effectively a softmax or some other function so that you are normalized. So it almost gives you like a probability distribution over the position. And now you just do a weighted sum of the values where the weight comes from the query key similarity, and you're just summing up the values weighted by that. It's a really simple idea, right? There's nothing crazy going on here. The math is actually very simple. And thanks for PyTorch and TensorFlow and other toolkits. Don't even worry about the gradients because they get computed somehow. You can actually implement this without writing, just using the pre-existing blocks in any of these toolkits. Okay, let's take another step. We talked about attention. Let's talk about self-attention. So the main thing that happened here is that the context went away. So now what you end up doing is you give a sequence. I'm going to treat the first position as context and do the attention over the whole sequence. That gives me a vector. Then I'm going to consider the second position as context and again attend over the whole sequence, and that gives me a vector. And I keep doing it for the whole sequence. So for each position in the sequence, I'm going to treat it as a query and attend over the whole sequence and repeat it for all the positions in my sequence. So what does it look like? You see, this is for the first position, this is for the ith position, this is for the last position. I'm just showing kind of the extreme version, right? So you're basically doing the attention multiple times, but each time you're considering each position to be the query and just basically repeating that whole attention process previously. So that's self-attention. I'm kind of jumping through here. So transformer is a neural architecture block, which effectively takes, let's say, a sequence of words like a text, applies self-attention, gets output, adds a bunch of other convolution layers. All of this is arbitrary. They just exist because empirically they work. There is no theoretical strong basis of what combinations you do this. And they've defined some neural block that's effectively just a chain of multi-headed, ignore multi-headed for now, self-attention, some batch normalization or layer normalization, some feed-forward convolution, and that's a block. That's the transformer block, right? But the key concept here is about self-attention. That's really the main block, and then they just combine it with some other layers and get a more composite block. So that's one part. I'm going to quickly say what language modeling is, and then we're just going to put these two things together and we'll get BERT. So language modeling is a concept in NLP. So you're trying to learn So what effectively, there are many different ways of learning language model. One is like you get a sequence of words and then you try to predict the next word, or you get a sequence of word and then you mask out some words and try to predict those words, or you get a sequence and then you try to predict the next sentence or the next sequence in your corpus. And the whole idea of learning language model is to basically understand that if I now arbitrarily give you a sentence, can you tell me how likely is it that this sentence actually came from the same language model that my corpus has, right? Or if I give you a sentence, we are 1.5 minutes over. I will finish in 2 more minutes. I can see Hussein looking at me like, what is this guy doing? So basically the idea is that you want to learn up those corpus statistics so that given an arbitrary sentence, you can say if it belongs to the same language model, or maybe given a sentence, you can figure out what are the other words that might come after, or some of the fill in the missing words. And this is a trick that people use to do unsupervised learning, pre-training a lot. And this is what brings in, so there was a whole piece of work where people realized that you can take, obviously getting labeled data is very costly, so you can take these language modeling, very complex models with billions of parameters, and then do unsupervised training, but just training in a language modeling setting on very huge corpus, like whole of Wikipedia and book corpus and whatnot, right? And what are these models that you're that you're training on this? So BERT is one of those models. BERT is basically nothing but a set of stacked transformer layers, so it's really simple. It has some more details that I'm not going to go in, but it's effectively, think about it's just a network with a bunch of, let's say, 24 different transformer blocks stacked one top of each other. You take the whole model, you pre-train it as in a language modeling setting over a huge corpus, and then you take the same model and then you fine-tune it towards the exact task that you care about, which could be search, IR, or it could be like, I don't know, parts of speech detection or some other NLP task. And effectively, the reason we are talking about this is this is a few months ago, what the MS Marco passage leaderboard looked like. So you can see I just Control F BERT on the page, and you can see what's going on. And you've seen the same thing on the Trek data that we talked about. So I'm going to finish here, but I'm just going to leave you guys another point. So we've also had some discussions earlier in the week about thinking about research problems. So I'm going to just plug in that if you're interested in this area, the Trek deep learning track will be back this year as well. We have a large data set. We are actually seeing a lot of exciting results coming from, so this is just showing why we were focusing on building a very large data set. We are at a point where, so this is where the data is, but the reason we are doing it is because we are seeing just the presence of these data and some of these big model inventions. We are actually starting to see some very strong results. So if you're interested, this is where the last year's data is, and we'll have something similar soon once we finalize for the track for 2020. So please do come and participate, and I apologize for going a little bit over time, Hussein, sorry. And to everybody else for keeping you away from lunch. We'll have the lab sessions after lunch today, in which we'll just plug, we'll go through how to handcraft a very simple neural network with one neuron. So that should be fun. And then Daniel's going to be leading the learning to rank exercise as well. So hopefully I'll see many of you guys at the lab session. Thank you.
To finalize his sentence, with respect to the lab session, because there are more people in the other session than here, we sort of counted heads. And we're going to switch the lab venue, so you guys will be downstairs in the Ishangor lab doing this.
Perfect.
It's better overall. And enjoy the lunch.
Thank you.
Need to make sure, yeah.
That's the problem. You need to talk about that.
Oh, really?
I've been doing those too.
Okay.
The projected downstairs does the evidence. It's fine. The projected yes, this is, did you see this one? This one for you guys, the unit to be serious spread times. So it's not good. Yes, yes. So those are chess.
No, you'll get another one.
That you can imagine.
Oh, yeah, sure.
Did we upload our final slides to the share?
I uploaded last night.
You didn't put it on like your
I uploaded last night. I don't think we have had any changes since then. Yeah. Like it includes the things you put in.
We had a last minute. We had a last minute edit.
Yeah, that's
That's